Swayam Prabha. Digital India. Educated India.
Hello, welcome to the first class of this course, E611. So the previous meeting was just to discuss the various aspects of this course, but here we formally start with the lectures. So first let me share my whiteboard. As I said in the last class, this course is about microwave engineering. So what is microwave frequencies? So the microwave frequencies are a special class of frequencies. Sometimes they are defined as 0.3 to 30 gigahertz. Sometimes it is also defined as 1 gigahertz to 30 gigahertz. Okay, first let me I think I have not shared my screen, so let me share it. Yeah, so now it's visible. So as I was saying, microwave frequencies are sometimes defined over this frequency range, or sometimes they are defined over this frequency range. Now, if I write the frequency versus wavelength for these, say if we start from this is frequency, this is lambda, and say I write the frequencies in gigahertz and lambda in meters. So for 0.3 gigahertz, the lambda comes out to be 1 meter. Now this follows from this formula, where c is the speed of light. This is 3 into 10 raised to 8 meters per second. Okay, then okay, let me okay, so 0.3 is 1 meter, and for 3 gigahertz the lambda value is 10 centimeter. For 30 gigahertz, the lambda value is 1 centimeter. For 300 gigahertz, the lambda value is 1 millimeter. So this follows from this equation. Now, what the microwave frequency, what is special about the microwave frequencies? You see that when the frequency exceeds 30 gigahertz, the wavelength is lesser than 1 centimeter. And in fact, we enter what is known as the millimeter wave range. So for frequencies which are higher than 30 gigahertz, the wavelength is lesser than 1 centimeter. It is in millimeters, and so that's why it is known as the millimeter wave range. So in here, when we discuss about microwave engineering, it is necessary to see the electrical voltage or electrical current in terms of waves. We cannot see them as, as normal constant sources anymore. It's at a high frequency. And then the other important thing is, at these frequencies, dimension of the wavelength is comparable to the dimension of the circuit. When you have your wavelength in centimeters, that is more closer to the common everyday objects that we handle. So what is the impact of this? Why is it that when we have dimensions of the wave compatible with the circuit size, why do we have a problem? The problem arises because let us say we have a simple board, okay, and we connect it to a voltage source, okay, like this, and say we connect the other end to the ground. Now, conventional Kirchhoff's law says that the voltage, say this is V of t. Conventional Kirchhoff's law says that all points on this metallic conductor, so this is a metallic conductor. Conventional logic says that all points on this metallic conductor will be at the same potential. However, what really happens is you will, instead of the voltage being constant everywhere, it will be in the form of a wave. And wave means it will have maxima, minima, then null points. So this point of the conductor, say, is at 0 voltage. This point is at maximum positive voltage. This point is at maximum is at maximum negative voltage. So that is the problem. We cannot have a circuit we cannot have a piece of metal which is at the same potential everywhere. So this is the biggest problem that happens when we have biggest problem we have to deal with when we have microwave frequencies in our circuit. So, what are some of the important frequency bands within this range? So I'll just write it down here. We have this radio, AM, FM, which is from 535 kilohertz to 108 megahertz. And we have TV, VHF, UHF, which is from 554 to 890. So these values are given in this table in the slides. You can go through it. And then the more common ones, for example, Bluetooth is between 2.4 to 2.5 gigahertz. And then at the extreme end we have collision avoidance radar, which operates at 76 to 77 gigahertz. So these are, again, this for particular application falls in the millimeter wave range, but still I am mentioning because they are also in use. Then we not only is the frequency, absolute frequency value important, sometimes we have standards like what is known as the ultra wide band, where the range of the bandwidth itself is quite high. So you see this ultra wide band ranges all the way from 3.1 to 10.6 gigahertz. So so now let us see what is a wave. So wave is a periodic motion of a point both in time as well as in space. So the usual equation that is used to represent a wave is given like this. Okay, where this T, capital T, is the temporal period, and this lambda is the spatial period. I think many of you might have taken courses where you have come across what is a wave, but this I'm still mentioning just for just for completeness, because this wave is something we will be handling, we'll be dealing with a number of times throughout this course. So if we can represent a wave like this and say this is the positive x direction, then the wave is given like this. You'll excuse me if my handwriting is not so good. I'm trying my best, but this stylus and this screen, they're not always so convenient to write. Okay, so now that we have established what is or not established, we have what is a wave. One important term that we frequently come across while discussing waves is what is known as phase velocity. So what is phase velocity? So again, writing that wave equation, just one correction. I think I made a mistake here. This should not be there. Just make this correction. It should only be a 2 pi here. Sorry for the slight error. So coming back to the wave equation, if suppose the phase of we keep it constant, so what does constant phase mean? Suppose we take 2 time instants of the wave. Now, for both these two cases, what you see is that the relative position is the same. That is, if the peak was here at time t1, then the peak is now at here at time t2. Now, the velocity with which this peak is moving, in order to compute that, let us consider the phase is constant. So if phase is constant, then that means what? It means so if this is constant and then we differentiate both sides with respect to t, what we get is so this derivative, this dx upon dt, this term is called the phase velocity. It is the velocity with which any particular phase of this wave moves. So when I say phase means we can consider, say, the maxima point, this point, the crest of the wave. What is the velocity with which the crest moves? Now look there, observe that this is not the real movement of any particle. This point if I draw it again, see, this was my wave, say for time t1, and say for time t2, this was my wave. Okay. Now this is for time t2. The blue represents time t2. Between time t1 and t2, the crest has moved this distance. But this is not a real movement of a particle. This point is just an apparent point. And that's why, because this is the movement of an apparent point, the velocity with which this point moves can exceed the speed of light, as we shall see for some cases. So that is a very important aspect of any when we discuss microwave theory. This phase velocity is a concept that we will have to come across very frequently. Then there are other effects that happen because of the wave. One is the diffraction. So diffraction means that constructive and destructive interference of waves coming from two different sources. So that is another important aspect of microwave engineering. I mean, so suppose you have a waveguide like this, and say, so let's just consider a rectangular waveguide, and say we are feeding it from two different directions. Now, conventional circuit theory will say that, you know, the voltage, the resultant voltage on this waveguide should be sort of, we have to apply the Kirchhoff's law and compute what is the actual voltage, see what current is flowing, compute the resistance offered by this waveguide. But in microwave frequencies, it's not like that. What really happens is that at this point, we will have one wave emanating, and at this point, we will have another wave emanating, and the resultant wave that will be actually transmitted through this waveguide will be depend on whether the waves are constructively or destructively interfering with each other. So that is one important part. I mean, we have to consider the wave nature of the voltage. So as we shall see, you know, that entire Kirchhoff's circuit theory, that entire circuit theory that you might have read, studied in your undergraduate courses, that is a special case of these of this microwave theory that we are going to study. Let us discuss some more wave effects that have to be taken into account when we discuss microwave engineering. So another effect is what is known as skin effect. So what is skin effect? Skin effect is like, suppose you have a solid conductor, then the depth to which the current is actually flowing through the conductor depends on the frequency. Now usually we assume when we have DC current flowing, we assume that the current density is uniform. But that is not the case for microwave ranges. In fact, this skin effect comes from electromagnetic theory. The depth to which the current will penetrate is given by this equation, where sigma is the conductivity of this conductor, omega is the frequency, and mu is the permeability. So as we can see, the more the frequency, the smaller the value of the depth. So that's the problem. So for very high frequencies, the depth, so say for a particularly high frequency, the current will exist only within this range. Okay. okay, only over this range. So because current cannot penetrate beyond this depth, so the effective resistance that will be offered by the waveguide will be higher. So the same waveguide will offer a higher resistance for a higher frequency as compared to a lower frequency. Then another interesting effect of wave is, which is the concept of what is the shortest path. What do I mean by shortest path? Now this happens because waves travel with different velocities in different media. So suppose you have a lifeguard. Yeah, let's consider a real life scenario and say there is a swimmer who is drowning at this point. Say this is water. Okay. Now the swimmer is trying to contact the lifeguard. Which path should he communicate with? Should it be this path, the direct line of sight, or should it be something like this? It might turn out, now the answer to this question will depend on what is the velocity of the wave or the sound wave that the swimmer is emitting in water and air. If the speed of sound, if the speed of the voice or the sound wave is much higher in water, then it might happen that this path, I beg your pardon, if the speed of sound is much higher in air as compared to water, because in this green path, the distance to be covered is more in air as compared to the red path, where the distance to be covered in air is less. It might just happen that the green path is quicker than the red path. So that is another criteria. What is the definition of shortest path? Is not so simple. It's not the path which has the least distance. It might be the path. It all depends on what is the velocity of the wave in the different media. So another interesting example of this wave effect as applicable to circuits is this classic example of a quarter wave transformer. So say we have a coaxial cable. So a coaxial cable has an inner conductor and an outer conductor, and say I short the inner and outer conductors. Okay, and say I connect a voltage source like this, and say the total length at which of this coaxial cable is lambda by 4 at the frequency of operation. So now if I will plot the voltage and current with distance, okay, so say this is 0 and this is lambda by 4, and because at lambda by 4 distance from the source, the inner and outer conductor are shorted, so the voltage here will be 0, but the voltage at the source end will be maximum. Similarly, the current here will be maximum again because of the short, but the current might be 0 here. So now this goes against our conventional theory, right? I mean, it's like if there is a short at some point between two conductors, then that should mean short for the whole circuit, isn't it? According to conventional circuit theory, if we had a short at the load end like this, then the short should also be here at the source end. But that is not what is happening here. And that is because of the wave nature of the voltage and current.